This is probably the closest we're going to get to a SIG-Network the movie this conference. So we're going to start off with a introductory session. So if you want to learn more about the network stack in Kubernetes and how it fits together, this is a good place. I'm going to step through a walkthrough of kind of the base components, take maybe a couple quick questions around each one, then move on to the next. Around halfway through the session, we're going to switch to a deep dive, which is more focused on some of the recent and ongoing work, and we're going to have contributors speaking to what they've been doing and what we're kind of planning for the next year or so down the line. So from a mile away, SIG-Network is just responsible for the networking related things in the cluster. This translates into a whole lot of things. We own a bunch of components, individual controllers. We own APIs. We own specs, so things like CNI drivers, we are trying to not maintain any. I think there's one that's being deprecated, but we maintain the specification of what is the CNI, how does it work, how should the drivers work. And then we own many fuzzier logistics, such as just how does the traffic move around in the cluster, how do the networking related things in the control plane work, and so on. So let's go through our walkthrough of the components, starting from kind of the base of the stack and moving our way up to the higher level things. So first off, if we just install a cluster, say we're doing something bare metal, this is what we get. We get some pods on nodes. And if you go and try to ping google.com or hit your other pod, you can't. And that's because you're missing the CNI driver, because there's not one installed by default. If you use a distro, there might be. CNI driver is responsible for actually handling IP allocation and dealing with routing from thing to thing. So the driver is responsible for managing your IP space, pulling down some IP, giving it to a pod, and then making sure that some kind of routing system and rules exist, be it like iptables or eBPF or some kind of cloud system, to actually get your packets from A to B. So maybe do we have any quick questions on the CNI and what it does? No hands? All right, so now that we have the ability to just hit other things in our cluster, that's pretty manual. We want to be able to do more than that. But also, we need to think about security. So there's a lot of misconceptions. I've talked a bit earlier this week about some of them around what can access what. So here's a graph if you've got 4 pods in 2 different namespaces as to what can actually communicate. And the answer is literally everything can. So even though we expose nice little primitives like short service names within a namespace, every pod IP is accessible from every other pod. And that's not ideal. We use something called network policy to help with this. Network policy is an optional spec that many CNI drivers support that lets you essentially add firewall rules to your pod-to-pod interlinks. The way network policies work is, by default, it fails open. So if you have no policies, then everything still can talk to everything else. As soon as you add any policies, we use selectors to point out pods that they apply to and specify ingress and egress rules. As soon as the pod is selected, it's completely shut down except for any rules. So the selector wipes out access, and then at that point, any additional rules you apply specifying that pod layer on things like whitelisting to let more specific things access. So in this case, we have a denial example. All we're doing is we're taking some pods that match app A, and because we're selecting them, we're now denying all traffic because we don't have anything explicitly letting traffic in. For those who aren't familiar, the label thing is a very, very common pattern in Kubernetes internals. Essentially, as a way of reflecting relationships or pattern matching, we have labels on any given thing. Using just like app is something is very common, but doesn't have to be app. You can use multiple. And then whenever we want to reference this, such as like a hierarchical relationship, we use those same labels and say all pods or all resources that match this, we apply to. So here's a somewhat more practical example of Ingress. We're taking a namespace that matches a team selector. We're taking a pod selector for A, and we're saying that for B, we can ingress. So You can't ingress to B except from this thing A in this namespace. And that looks like this. This is a much more realistic, well, subset of what your service graph likely looks like, because there are probably very few things in your cluster you actually want to expose to everything in the cluster. In reality, you have some kind of a complicated digraph of what is actually interacting. This is also something that a lot of service mesh functionality and so on exposes in similar ways. So any questions briefly about network policy? Quiet crowd, all right. So next up is endpoints. We want to make pod IPs more accessible. If you've ever had to manually deal with, I have a fleet of VMs, how do I connect to them all? You'll understand very well why we want something more than just exposing raw pod IPs. Endpoints provide two sets of abstractions for us. The first one is just that it's a list. So we have one object with a whole bunch of IPs. We don't actually have to list all the pods and scan through them. The other thing is it includes the pod health checking and so on. So if a pod is not ready, it's not in the endpoints. If a pod is ready, it is. In this way, we just have suddenly a list of everything that's ready for traffic that we can then easily consume in our service discovery or use to populate a load balancer or something else. Questions about endpoints? Okay, from this point, yeah?
When the endpoint is created, does it guarantee that the pod is in the ready state? Like, let's say if the controller watches for endpoint creation event. When it sees create event for endpoint, so the corresponding pod is absolutely in the ready state, right? Or
sorry. Thank you. Oh, sorry about that. Question was, when the controller, which is observing, let's say, endpoint create event, sees the create event, does it mean that the pod providing that endpoint is in the ready state? It's a guaranteed. Or controller needs to basically double check that the pod is in the ready state?
I'm pretty sure it's when the check is ready, but I would appreciate clarification on that. Right, wrong?
There are actually two lists in the endpoints structure, one for ready, one for not ready. So you don't need to worry about it.
Thank you.
Another question here.
So I have a related question on the previous slide. We saw the policies. Yeah, so this kind of structure, so who or where is it enforced? Is it enforced at the CNI level? So we see the pod descriptor, it is passed on, but I believe probably the controller doesn't do much about that, it just passes it on to whoever implements the network. So is it handled at the CNI level, enforcing the policies, or where are they implemented? Which level?
This is enforced by the CNI drivers, but because the network policy is not a mandatory part of conformance, not every single controller does support it. But this would often translate into like not making a rule in Google Cloud or not programming in iptables rules if a certain path isn't allowed.
And there are also a bunch of third parties that can implement network policy independent of networking. So you really need to put together a comprehensive network plan.
All right, so on to the next. I guess just re-clarification on labels, already kind of touched on that. It's just the way that we are referring to the kind of hierarchy of things. So when we have our set of pods, we also have a label specifier in our endpoint set specifying how we actually pick which pods we're watching for their readiness or lack thereof. So because, again, just consuming a raw endpoint set, it's better than having to watch all the pods, but that's still not super out of the box useful because you have to actually coordinate everything. So a lot of the time we just want a load balancer of some kind. We just want to hit one thing and not fuss about it at all. So services are the answer to that. Services program up a load balancer, the behavior and logistics of which vary, and point it at all the endpoints. In doing so, they also create an IP, again, the origin of which varies, and includes that in the service. So now you have one single IP to hit, and the service controller is now continuously making sure that all the ready endpoints are programmed on the load balancer. Now, there's a number of ways that this works. For a start, there are 4 different kinds of services that all behave a bit differently. First one I'll mention because it's very simple is type external name. And it's basically just a CNAME if you want to use that mechanism to expose an alias. It can be a CNAME to anything, including some random domain outside your cluster. The next kind, and probably the most common kind, is a cluster IP. Cluster IP allocates some IP within the Kubernetes cluster and then has an internal load balancer. So I'll talk more about one implementation in a sec that we have for that built in. Next type is node port. It exposes a specific set of ports across all your hosts and then relies on direct ingress from there. So this would be if you want to say, have some external load balancer or some external service discovery just pointing easily at your nodes, something usually from the outside. And the last kind is a combination, essentially, of cluster IP and node port. It's type load balancer. It's basically the most primitive form of ingress you can get, where you are, at least in terms of the constructs, where you are opening node ports and you have a cluster IP. So you hit a given node port on some machine, and then you get routed through the cluster IP load balancer to your pod. This does have some downsides because you are routing around a little bit within your cluster. There's a better alternative that I'll talk about later on. Questions so far about services? I'm making Tim work here.
There's a mic here too, by the way.
Thank you.
So the last one that you mentioned, load balancer, or I don't know what it was. Why would you ever use that instead of node port if it's just node port plus more? Like that doesn't get you anything.
It gets you the more. So you don't necessarily have to rig up the load balancer yourself because you can rely, if you have like a cloud provider integration or something, on them to spin it up for you. So this would be a way to just get like a TCP load balancer spun up for you. That gives you ingress into the cluster. Yeah, up front.
How much control do we have over How much control does the user have over the load balancer for the cluster IP?
I'm not entirely sure. I believe it mostly depends up to the implementation of whatever service controller there is.
There's, at least out of the box, the cluster IP is a range that you give to the cluster at creation time, and then it's either auto-allocated or you can set it, and it will try to get it. And if it can't get that one that you wanted, I'm sure there's an error, right? There's an event.
The address. I'm asking about the actual load balance.
The actual, you mean how the traffic is split?
Yeah.
That one is not currently part of the API except for external traffic local, which governs whether the traffic is going to be routed to your local node or across your nodes.
So it's not part of the API. You can control it by, if you can configure your load balancer itself, like Kube Proxy, which is a built-in implementation. You have a lot of different knobs you can tune around how it works. And there's theoretically some load balancers that let you use annotations to add extra features.
Yeah, thanks. Do we still, like, canonically, I remember we used to have, like, the cloud providers all used to use, like, there'd be everything would use node port under the hood as, like, the glue. Like, I remember at least GCE or GK used to do that. Is that still normal to use node port under the hood for what your TCP load balancers directly talk to if you're in the major clouds?
So actually, GCE does not use node port because there's this it can balance the VIP directly onto the VM. I know AWS used to, maybe not anymore. Maybe not anymore. Right. And then there's, at least, I can mostly speak to GCP. GCP has this notion of network endpoint group, which is, which basically, for certain types of load balancers, it can go directly. So it doesn't need to transit via the node port to get to the service. Yeah. So in some sense, it's up to the implementation whether or not it actually needs the node port. Some do, some don't. Yeah.
Yeah, node port with type load balancer is common, but not strictly required by any spec. So if you expose pod IPs directly on your network, like I think that's a common Google behavior. At Lyft, we use a CNI that does that. Then you can directly program up individual pods on your load balancer. And that's also usually way faster because you're not translating through anything. You're directly going to your instance.
Does the cluster provide any mechanism for the load balancer to provide a feedback about the health status of the endpoints, or it is the responsibility of the load balancing implementation itself?
There's health provided about the load balancer itself, but I don't think there's anything in the spec that directly provides endpoint level feedback.
So depends on what kind of feedback you want, but just earlier this year, there's a feature called Pod Ready. It's either called Pod Ready++ or Pod Readiness Gates that basically lets the infrastructure. So when a pod is coming up, it first comes up and then it becomes ready. The question might be, okay, if your pod is participating in a load balancer, how do you tell the system that that pod actually hasn't been programmed yet? And basically, pod readiness gates is an additional gate that the infrastructure can add to your pod to say, okay, only when the load balancer has programmed this pod, then say, flip this gate to say, okay, this pod is actually ready because it's not only just ready from a local level, but also from a network infrastructure level.
Essentially, it's a way to make sure that my pod is on the load balancer is considered part of the readiness check. So consider if you didn't have this, I want to go and rule my deployment and update my app. Okay, all the replicas are replaced, but programming the load balancer takes a minute and everything's swapped out. So suddenly from the perspective of my load balancer, everything's down. So that's why the readiness gates are critically useful, is because we can introduce that extra concept of is it ready without needing to get in the way of the path of the health check. Because otherwise you can have a can opener in a can situation, because if you try to block the health check, then you can't necessarily route traffic to it.
I will just add to that I think this is a place where we can do better. Been looking at a lot more higher level networking systems later, like load balancers that really want their own direct to endpoint health checking, and our APIs don't fit the bill for some of these.
Yeah,
so I think this is an area for growth this year.
We provide the building blocks, but it could be more powerful and it could be a little bit less mechanical.
I saw a hand in the back there, Bowie. It's on you.
Oh, all right.
Is it just the first packet that hits the load balancer, or is it the session stickiness that every packet goes to just a single end destination, like say 1.1.1.1?
Sorry, you're asking if there's a single destination?
So you have multiple pods running behind this load balancer for a single application. Would there be any session stickiness at the load balancer end, or would it be just the first packet that would be hitting the load balancer, and then after that the packet would be reaching directly to the pod?
I can take that one. So I think there's two questions here. There's one of stickiness. So there is an option in service for stickiness that is based on the 5-tuple, right? So client IP port protocol to the server IP port. So you can establish that if you want it. The rest of the question is about, I think, about performance and like whether the load balancer touches every packet. That depends on the implementation. So if you're looking at the default, like the iptables implementation, which is based on iptables NAT, that will look at the first packet, establish the connection, make a connection tracking record, and then ignore the rest. Other implementations might do something different.
All right, I think we're getting more and more questions as we get to more of the.
One more, sorry. So what if you have configured session stickiness and the endpoint dies or the port dies? What happens in that case?
When we detect that that endpoint has been removed from the endpoint set, we will remove any, I think we remove any connection tracking records that were related to that endpoint so that you'll have to pick a new endpoint. Basically, your stickiness gets lost. At least that's the default implementation.
Yeah, a lot of the specifics do wind up being however the load balancer works, because the spec doesn't control the load balancer at a fine granularity. It just provides the basic programming details. So services and endpoints are designed as a way to provide potentially custom solutions, but there's one that many, many people use if they're not using a service mesh, and that's Kube Proxy. Kube Proxy is our built-in service implementation that programs things with a couple different modes. Most people use iptables, and it deals with assigning the cluster IP in terms of network rules and then forwarding to all the backends. So in iptables mode, it's actually kind of funny if you look at it. We basically create a redirect on the cluster IP to a whole set of IPs, all with kind of different weights getting more and more likely. And that's the very kind of interesting approach to doing random distribution. There's IPVS mode, which lets you do like real round robin routing and more advanced things. Yeah. Thank you, Tim and Bowie, for the running around.
So the question is around Kube Proxy and iptables and IPVS mode. Let's say I have some custom OVS kind of based implementation. Would it be possible to write a Kube Proxy plugin to like program all these kind of iptable rules as connection tracking rules in the OVS? Is there something like a plugin to Kube Proxy that we could write in the future?
As the maintainer of Kube Proxy, no. I don't want to build it any more monolithically than it currently is. I'd rather have people fork it and build a separate one that does exactly what you need. Basically, there's way too many config parameters that need to come into Kube Proxy to cover all the different proxy modes, and it's become very confusing for people. And I would rather see people sort of verticalize and go build their own thing. So I basically put a halt on new proxy modes. In theory, you can do what you're talking about, but I'm encouraging you to do that in a separate code base. Oh, and sorry, and by the way, there was a new implementation of services launched this week. Some of the folks at VMware launched something called Entria. I hope I get the name right. It's an OVS-based implementation.
So, DNS. If we have a pod, we can nicely route to one of our names, like MyApp or Nginx or Redis. And there's a reason that all that magic works, as well as a lot of the cluster internals, and that's because we inject DNS routing information. So when the kubelet starts up a container, the kubelet being the component that actually manages containers on the host, we program in some service endpoint where DNS is supposed to go. Those DNS requests are then routed to some DNS service normally running in the cluster. Like the default that's shipped is a core DNS deployment, but you can customize how that works, and you can also pick a different DNS setup if you so desire. Dare I ask questions around DNS? All right, thank you for that. So the one that I suspect everyone's going to have a question on is Ingress. Ingress is our kind of top level HTTP 7, or not HTTP 7, layer 7 HTTP way of having and composing cluster traffic that's from an external source. so going into the cluster. The way Ingress works is we define a set of HTTP backends using potentially rules like host names or paths, and then correspond them onto some service. So there's a couple of nice things about this. One is just that it's a way to actually do your layer 7 routing in a config. So instead of writing a custom Nginx deployment and making sure that you have to update your Nginx deployment to route out to your services, we provide a more Kubernetes native way to do that. The functionality of Ingress really, really varies depending on what controller you're using. So later in the session, we're going to be hearing more about like what's wrong with Ingress, how it's going to get cleaned up in the theoretical V2 future. But right now, the exact rules that you can use vary provider to provider. And if you've ever, especially had to use different providers for Ingress, you'll see that there's all these custom annotations that let you define things like TLS or a named IP from some pool or algorithms or security settings or cache settings, and it's all different. And that part is kind of unfortunate because it's one of the more sticky pieces as soon as you go from cloud to cloud or system to system, or even just if you want to like switch over to cheap Nginx in-cluster stuff. So questions about Ingress. I'll specifically defer future of Ingress questions for the next talk. All right. Here's an example of us composing some very simple rules. We have our main path, so we default to some particular backend, and then we have an API backend where everything that matches that HTTP path gets routed there. So much nicer, at least, than having to have a custom router in your cluster for this. So that's an overview of what's in the networking stack. I'll touch briefly on some of the stuff that's been going on lately. Two definitely biggest pieces of news, we even heard about them in the keynote, is IPv4, IPv6 dual stack is now available and is continuing to progress. That's been a huge, huge effort for a long time, and it's been a notable piece of work in the SIG since this spring. I think almost everyone has chipped in some way with that effort. Another big one is also the endpoint slice change, where we enhance the ability to scale up clusters to have more nodes and or more pods by reducing the traffic churn that happens. That's something also we'll hear about in the next talk. As far as upcoming work goes, future of Ingress is a big one. Ingress was beta for a long, long time. At this point, it's effectively GA, and we need to figure out how to polish it up, officially GA it, and then kind of move on to building better systems. And we don't have very particular plans here yet, but we are looking more at the future of multi-cluster networking and trying to figure out how to make that work better. So if you want to get involved with the SIG, it's relatively easy, dare I say. I got involved first a year ago at last KubeCon North America. There's a couple different ways we communicate. Slack and probably mailing list are the best ones. Didn't actually put a link here to the SIG-Network info page, but if you just Google Kubernetes SIG-Network, you'll find us. We also have a bi-weekly hourly call on Thursdays at 2 p.m. where we kind of talk in person about anything that requires a bit more coordination or agreement. So if you want to check things out, I'd recommend subscribing to those and maybe just shadowing a call or two and kind of seeing what's going on. Promise we're a friendly bunch. You can see Laki in his Halloween costume there. Oh yes, that's the one of the Starfleet engineering uniforms. Yeah. So also, if you want to check out like just units of work and dive in, really helpful if you can help review PRs, especially if you're a pretty good code reviewer. It helps to understand the stack very well, but there's a lot of things that are easily transferable. Or look at issues, see if you can triage them, verify them, maybe even work on a solution if you don't think it's going to be too challenging. So in GitHub, we have our Kubernetes repo, and everything that is for the SIG is labeled the SIG-Network in the issues and the PRs. Also, my advice as someone comparably new is do start small, because a lot of this stuff is much more complicated than you probably think, and because this is a big project with a lot of tech debt and many, many users, there are many things that are conceptually simple and in practice are not. So yeah, if you want to find us, here's how you do so. So we'll probably have a pretty quick break and then bring on the next speakers to go into the deep dive. Thank you.
So this is the SIG-Network deep dive. I'm Bowie.
I'm Rob. I'm Dan.
And today in Barcelona, I think we did a SIG-Network deep dive, and it was really deep into some of the topics that Vallery had covered in the first half. But today what we're going to do is deep dive into what is new in the networking space. And we have about 5 topics that we're going to be covering. One of them is endpoint slice. The second one is the Ingress API and service in Ingress API evolution. Then we cover dual stack, service topology, and on everyone's mind, SCTP. No, it's a very important protocol. So endpoint slice.
So endpoint slice is a great new feature in Kubernetes all about making endpoints more scalable. But to understand endpoint slice, we need to understand a bit of background of how we came to endpoint slice, how that was the solution.
Excuse me, which one of you is Rob, which one's Dan?
I'm Rob.
Dan. Okay.
So Kubernetes clusters just keep on getting bigger. Kubernetes is successful, it's great news, but along with that success comes problems of scalability. And endpoints became one of those bottlenecks. Each network endpoint for a service needs to fit in a single endpoint's resource. Now this works great up to a certain point, but when you start to get services that have lots and lots of endpoints behind them, let's say you have thousands of pods, you start to run into some real scalability issues because all of those endpoints stop fitting in a single resource. There's a real size limit, etcd default size limit, that just prevents that from happening. By default, that's somewhere between 5,000 and 10,000 network endpoints, depending on a few different configuration variables. But at that point, you just run out of space in your endpoint's resource. Now you could modify the configuration and let that get even bigger. But the problem is that doesn't really help anything because we have a second problem that is very related to that first problem. And that's that any change to the endpoint's resource needs to go to every single node in the cluster. And that's not great. So in a 5,000 node cluster, a single endpoint change could result in around 5 gigs worth of data being transferred. So just think about DVDs worth of data going out every single time a pod changes inside your cluster. It's not great. Admittedly, not that many people are running clusters this big because it's not great yet. But endpoint slices are set out to try and fix that. So the idea behind endpoint slices is really simple. We have this huge endpoints resource. Instead, we have smaller endpoint slice resources that are really just slices of endpoints. Really simple. So here's an endpoint YAML, because we all like YAML at KubeCon. Here's what an endpoints resource might look like. You probably haven't interacted with this very much because it just kind of happens behind the scenes. You have a service, you have some pods matching that service, and behind the scenes there's an endpoints controller that runs through and tracks all these IPs for those pods and keeps track of them for you. And like I think Tim mentioned earlier, there's an addresses field and there's a not ready addresses field. And these are just both lists of addresses that are either ready or not ready for your service. So it's a really simple concept that works really well to a certain point and then starts to fall apart. So with endpoint slices, it's a similar thing, just with a few extras added in. You can see that we've added an address type now. So IPv6 is a supported address type, as an example. Additionally, we've added some labels because with endpoints, we had this really simple thing where you have one endpoints resource and you have one service. So the names are the same, everything maps directly, it's really easy. Because now you have multiple endpoint slices for every service, you have to do a little bit more work to reference the service that an endpoint slice belongs to. So in this case, we have a label referencing the service name, and we also have an owner reference that I have not included here because it would make it completely unreadable. But an owner reference pointing back to the service as well. And there's a few other differences I'll cover shortly. So one of the big additions with endpoint slices is we specify and validate IP addresses. So we have address types that are IPv4, IPv6, and FQDN. Eventually, we may add more address types, but for right now, that's where we're starting. And for a given endpoint slice, you know that addresses in that slice are going to be valid IPv4, v6, or FQDN, depending on the address type on that slice. Ports also now have an app protocol field. So we already have a protocol field on all ports in Kubernetes, but that's L4, TCP, UDP, et cetera. Whereas with this app protocol field, you could actually specify something like HTTP, which hopefully will be useful for consumers of an endpoint slice API. Endpoint slice also switches around what we're doing with conditions. So before we had just a list of addresses that were ready and addresses that weren't ready. So if you wanted to add any additional condition or information about an endpoint, it was actually pretty difficult. So we've switched that around to add a conditions field on every endpoint that right now just includes a ready Boolean, but could include additional information about the condition of a given endpoint in the future. And additionally, endpoint slice endpoints contain topology fields. Currently, that's node name, zone, and region, but arbitrary information can be added here very simply. It's just like a labels field, just specific to topology information. And finally, a key point here, this is not enabled by default in any Kubernetes cluster. In 1.16 and 1.17, you need to use the endpoint slice feature gate to enable this.
But it is beta.
It is beta, that is true. So let's talk about performance, because the whole reason we went through all this was to try and make this scale. And the great news is the first implementation of the endpoint slice controller worked well at scale. It was fine. It actually performed a little bit better than the endpoints controller. But that wasn't actually ever the real bottleneck here. The real bottleneck came with Kube Proxy and bandwidth. And I'll say data transfer is dramatically lower, but Kube Proxy was still a bit of an issue because it's a little bit more complicated now. So I needed to do some testing, some scale testing to see what we could improve. And my basic methodology here was to spin up a cluster with kubetest, modify the Kube Proxy manifest just to enable profiling, and then use kubectl port forwarding along with pprof to actually profile Kube Proxy. And this is actually really, really helpful if you're ever trying to debug anything in Kubernetes and understand why things aren't as fast as you might expect. My colleague Minhan has a really cool tool called KubeScript on GitHub that allows you to push custom builds of Kube Proxy to specific nodes in your cluster really easily. If you're debugging Kube Proxy or other networking tools, I highly recommend that. And so what I would do is I'd have a whole bunch of different versions of Kube Proxy running in the same cluster on different nodes and compare their performance. And the final results I'm going to show were gathered on a 150 node cluster over a 15-minute window, scaling from 0 to 10,000 endpoints for a service. And I used 4 versions of Kube Proxy. Kubernetes 1.16, 1.16 with slices enabled, and the same for Kubernetes 1.17. So, before I get to the actual charts, let me show you the 3 changes I made because they ended up being significant. The first one was I was using endpoint.ip for sorting, and that ended up being an incredibly expensive operation. I had thought endpoint.ip must just get the string and return it. The actual string in the endpoint object was a IP port combination, so it was calling netutil to parse an IP out of that and then returning a string. So that was very slow, and I was using it for sorting and not good. So 41% of total CPU time was spent calling this single function. Not great. So I changed that just to use the string that already existed, and this went away. So on to the next problem. So there's this cool thing in endpoint slice cache that transforms a whole bunch of endpoint slices into a data structure called endpoints map. And this is the data structure that Kube Proxy uses behind the scenes to actually render proxy rules. Whether that's iptables or IPVS, they both use this data structure to actually render the proxy or rules. And this was called on each endpoint slice update. Now, that's about how endpoints work before it, which is fine. But the problem is it's a lot more complicated to merge a whole bunch of endpoint slices together and then actually transform them into an endpoints map. So this really didn't need to happen on every single endpoint slice update. This data structure is actually only used when the proxier runs. And at scale, there can be a whole lot of endpoint slices being updated between proxier runs. As an example, you can get many, many endpoint slice updates every second, and proxiers may only run every few seconds. So there's a significant difference here. Changing this logic around so that we could only compute this when it was needed ended up being a significant savings. And finally, there's a detect stale connections function that was taking, after these previous fixes, a whopping 82% of total CPU time, and it was being called on every single connection, even though it was only actually useful for UDP connections. So this was kind of a big deal. And I imagine for most people, they have at least some TCP connections in their cluster, if not most. So if that's the case, we're wasting a lot of time on something that didn't need to be called. Now, we didn't actually have information about what protocol was here at the point, but just changing some things around so we could have that information ended up being a very significant savings. All right, so that's the three things I changed. Let's get into the effect that had. So memory, it's an improvement, kind of. The two low lines there are the new 1.17 implementations, and the two slightly higher lines are the 1.16 implementations. So maybe a 20% improvement, maybe, but it could also just be noise. So this isn't a huge sample size, but there's probably some improvement here. Now, CPU usage was a little bit more dramatic. My first endpoint slice implementation was not great, it turns out. That big yellow line that continues 3 minutes after all the other implementations are done is my initial endpoint slice implementation. So not fast, and the rest are significantly better. But you can see the line, the trajectory that initial endpoints implementation had. As it scaled, it kept on getting slower and slower and taking up more CPU utilization. So even our baseline was going up at a pretty rapid pace here. The two lower lines are the 1.17 implementations, one representing endpoints and the other slightly lower one representing endpoint slices. So this is a fairly significant improvement. And where I think it really becomes more obvious is if you look at the pprof numbers we're seeing here, which are related to CPU time spent over this entire window. And endpoint slice, the initial implementation, is an absurd number there, but even our initial endpoints implementation is pretty slow compared to our newer implementations. And finally, to put this into a bit of perspective with some real numbers, we improved performance from the baseline in 1.16 around 20 times. This is only really, I'll give a little bit of a caveat here. This is only really going to be noticeable when you're operating at scale. When you've got a few hundred endpoints in your cluster, doesn't matter that much. But when you start to get into the thousands and tens of thousands of endpoints, this is going to be a huge difference. So that's what we found with some relatively simple Kube Proxy performance improvements. So let's talk about the endpoint slice timeline and when you might actually get to use this, when it might be enabled by default. The design was actually proposed in Barcelona this year at KubeCon. The KET was created in June and approved in July. We got our first alpha in 1.16, and it was actually released as beta in 1.17, but not enabled by default. We're hoping that we can get this enabled by default in 1.18, and if that all goes well, maybe we'll get GA sometime in 1.19, but that's admittedly optimistic. So, there's lots you can do to help us with endpoint slices. First off, does it work for you? Can you break it? Are we missing something? We want to get this out there. There's some great improvements along with it, but to really get this enabled by default, we need more people using it. So, please test it out. And speaking of testing, if you have ideas for how we could test this better and make it more thorough, definitely interested in better tests for endpoint slices. And then maybe the biggest thing of all, we want to migrate the use of endpoints API over to endpoint slices. So this includes things like the Windows implementations of Kube Proxy, Ingress controllers, DNS, and probably other things that I haven't listed here. But with that, I'll turn it over to Bowie to talk about Ingress.
So in terms of every API evolution that we want to do in the system, we first have to kind of look at the landscape and how it has changed from sort of when it was originally designed to what it is today. So on the hopefully right-hand side of this diagram, we have kind of the landscape of proxy LB providers and controllers. So I kind of loosely categorize these into cloud LBs, middle proxies, and transparent proxies. And as we see that the functionality of all of these is slowly converging in terms of what they can all support, but it's a slow process. On the left-hand side, we see that as clusters become bigger and bigger, for example, in the case of endpoint slice, is that there are more complex roles and personas involved in kind of deployment of applications on a cluster. In the early days of Kubernetes, we really focused on the empowered developer, who is going to be a single team that's going to self-service most things. When you get to bigger and bigger clusters that are shared among multiple teams, now these roles have been split up. And as an example, some of these personas may be an infrastructure provider. This is someone who owns the cloud environment. For example, setting up the cluster environment itself. Then there is the cluster operator who operates the cluster and enforces policies globally across the cluster. Or maybe NetOps who enforces policies across all of networking. And then finally, we have the empowered application developer. So the key behind API design is to kind of think about how this evolving landscape then translates to APIs. Now, talking about Ingress, Ingress is actually a pretty popular API. It has very wide support among different implementations. And for some of the cases, it's actually good enough for a non-trivial number of users. So from a SIG-Network standpoint, Ingress is still a very valid API. And the plan is to clean up the spec and take the type to GA. Did you know it was still beta? So what are we going to do for the Ingress API? So clean up the object model. So as you saw on the diagram before, there's this new resource called Ingress class. In fact, every single Ingress implementation has an annotation that says, okay, which controller should be in charge of this Ingress, whether it's an Nginx or it's a cloud provider and so forth. So actually make that a real resource. The next thing is to tweak and fix the specifications. So we have a list of sort of minor discrepancies between how it is specified or maybe underspecified currently in the API and what the actual behavior we see of all the different implementations out there. There's some field renames like backend to default backend. The path and host name matching, actually the implementations we find do not sort of follow what is in the comments in the types.go. So we're kind of cleaning that up. And then finally, we add a bit of flexibility that will be hard to change later in the GA API, which is to enable you to not just route from your Ingress to a service, but also potentially target an alternate backend. However, for the first cut, we would expect controllers to only support the service type. Now let's talk about evolving this. So as I said before, we had a slide with kind of the changing landscape. So what does this mean for the goals of an Ingress API evolution? And remember, everything I say here is super early proposal, and the point of KubeCon is to get all of you, users plus implementers, to give us feedback. So we see at the high level 3 main goals. One of them is looking at those personas is to better model them with the resource model. The second one is, as the implementations all converge in capability, is to support more modern load balancing features. And then we did an Ingress survey, user survey in 2018, and we came back with 2 opposing viewpoints. One of them is that it must be portable, and the other one is I must be able to use all my power features of my underlying implementation. So portability is key, but maybe not just portability, but sort of predictability for the user. Can a user predict how portable their thing is and then not limit them if they want to go out of that spec? Finally, sort of build into the API standard mechanisms for extension, not just for API growth, but implementation and maybe vendor-specific behaviors. Because one of the feedback that you could see from the survey is, if I am actually a power user, don't limit me. I know what I'm doing. So this is a sketch, and this is sort of an evolving API, but what I want you to take away today is sort of look at this and get a general sense and work through your use cases, whether or not this setup makes sense. So generally speaking, we have 4 resources here. There's a gateway class, a gateway, a route, actually many types of routes for each protocol, and then your Kubernetes service. And I'll go through kind of describing what the role of each of these resources is in your cluster. So at the very top, we have gateway class. Gateway class is very analogous to Ingress class. This is intended for the infrastructure provider to provide different kinds of load balancers that are available to the user of the cluster. Now, in this example, we have 2 gateway classes. One of them is Internet LB, and the other one is Private LB. And in this cooked up example, when you create a gateway of Internet LB class, that represents that the user intends to export that service as an internet available service. And then if they use the Private LB class, that means that they are intending to perhaps export their service to their local VPC. Now next comes gateway and route. So gateway is sort of the linchpin of this API. Gateway is the thing that when you instantiate a gateway, it kind of wires everything up. Now what gateway contains is sort of a concrete manifestation of an instance of load balancing. For example, if you were on a cloud provider and the gateway class was provided by the cloud provider, creating a gateway will then call a bunch of cloud APIs to wire your load balancer up. Additionally, if you were on, say, using an in-cluster implementation of Ingress, but now gateway and route, it will then instantiate and do the configuration to sort of provision your load balancing. And then finally, this green box is the route. This is the application description that will be controlled by the application team. And because all these are 3 different resources, we can kind of attach different roles to them. For example, infrastructure provider will get RBAC for a gateway class. The NetOps perhaps want to restrict how gateways work, so they get the gateway, and then the dev team could get the HTTP route. Oh, you can still have self-service. Basically, you would give the dev access to gateway, HTTP route, and then maybe in the most extreme case, you could get gateway class, gateway, and HTTP route. So kind of, this is still early. We have these links don't work if you're looking at them, but when the document is shared, you'll be able to click on them. Also, these are also on the SIG-Network mailing list. So sort of how to get involved. This is still very early stages, and really, we really would appreciate feedback from users and implementers. And there's a working group that's going to be started. It's coming soon in terms of the info. We intend to have bi-weekly meetings, use the SIG-Network mailing list for now, until people tell us we're spamming them too much. And then also create a Slack channel, and there will be a repository in which all the spec working issues will be held. So really, this is feedback on the proposal. We want to hear from users and implementers. In fact, when we had the session that we on Tuesday, I think, we went into a deep dive, and there was one user, thank you for coming, But it was very helpful to hear their voice. And of course, we want to see experimental implementations as well. So moving on to dual stack.
Dual stack is a really exciting feature of Kubernetes that is starting to see some life in the form of an alpha release. To understand what we mean by dual stack in Kubernetes, we need to run through the goals for dual stack in Kubernetes. And that is that pods should be able to support both IPv4 and IPv6 addresses. They should be able to communicate IPv4 to v4 or IPv6 to v6. They should be able to access external servers on IPv6 or IPv4 addresses. And the same pod should be able to be targeted by either an IPv4 service or an IPv6 service. Node ports and external IPs should support both IPv4 and IPv6. As a departure from that, services, endpoints, and endpoint slices will all either be IPv4 or IPv6. They will all be an individual single family. And of course, with all of this, we want to ensure we're maintaining backwards compatibility with IPv4 only and IPv6 only clusters. So as you can probably imagine, dual stack is a really complex feature to implement. It's a huge project, and it affects lots and lots of things across the Kubernetes ecosystem. As an example, service, ingress controller, endpoints, endpoint slices, nodes, CRI, CNI, runtimes, cluster configs, and if you think about anything in Kubernetes that touches an IP, related shell scripts, whatever it happens to be, all of these things will have to change to support dual stack. So there's a lot of work here, and that means there's lots of opportunity to help. But let's first talk about the alpha release of dual stack. So first release for alpha was 1.16, and we got some updates in 1.17. All functionality is hidden behind a feature gate IPv6 dual stack, and the changes involved right now are that pods will have a new pod IPs attribute. So that pod IPs attribute will contain both an IPv4 and IPv6 addresses. Services have a new IP family attribute that will either be IPv4 or IPv6. Endpoints will contain addresses matching only the service IPs family, and endpoint slices will behave similarly, but they also have IPv4 and IPv6 address types that add an extra layer of validation there. So let's take a look at a simple example here. We've got a pod that has both v4 and v6 addresses, and we've got a service that we created that matches that pod, and it's assigned a cluster IP that is matching its IP family, so v4. And then, because we have a service that matches a pod, we have an endpoint slice that gets created automatically for us, and that pulls the IPv4 address out of that pod. Now, similarly, if we want to have an IPv6 service matching the same pod, that's also possible. So we've got a service with an IP family of IPv6, and it's got a v6 cluster IP. And automatically created for us, we have an endpoint slice that pulls the IPv6 address out of the pod, and that represents that endpoint slice. So that's a very high-level overview of how dual stack is going to work inside Kubernetes. And I just used endpoint slices here, but of course the same is true for endpoints. So a huge part of all of this is Kube Proxy needs to support dual stack for any of this to work. And I think it was Cal who had the idea to use some kind of meta proxier design, which basically involves running separate proxiers for each IP family. Instead of making huge changes inside each proxier, just pass either fully IPv4 addresses into a proxier or fully IPv6 addresses and endpoints into a proxier. So you have two running in parallel inside Kube Proxy, so two implementations of iptables or IPVS or whatever it happens to be, and those endpoints that match that family are automatically sent to that proxier. Currently, that implementation is limited to the IPVS proxier, but there's some great work underway for iptable support, and although there's no support for Windows proxiers, I think we hope that can happen soon. So have to cover some of the timeline of dual stack, and thank Dan for actually filling all this out, because there's a lot of timeline when it comes to dual stack. This goes back way before I was involved in Kubernetes, 2014, for the very first bits of IPv6 support. And the initial IPv6 single stack efforts began in 2017, and 2018 we hit a dual stack proposal that eventually turned into a KEP, and eventually resulted in the 1.16 release that included alpha support for dual stack just this August. So we're making progress. We're hoping we can get to beta relatively soon, but there's a lot of work to do, and there's lots of opportunities to help. So Kube Proxy still needs a dual stack implementation for Windows. Additionally, for what has released, we'd love feedback, testing. Does it work for you? Can you break it? Or anything we've missed? And additionally, because endpoint slices are also new and not enabled by default, does this all work well when we have endpoint slices and dual stack working together? And finally, is there anything in this implementation that we missed along the way? And I'll hand it off to Dan.
Service topology. This is something that is also relatively new in Kubernetes. We've been talking about it for probably a better part of a year, and even just last week some cool stuff happened, so we're starting on that road. But at its base, service topology tries to answer the question, how can I talk to a pod that's as close to me or as local to me as possible? So the problem that we have there, though, is what does local really mean? And it turns out that local means many different things to many different people, and it definitely depends on your infrastructure, how you set your cluster up, possibly what your networking solution is, all different kinds of things. So we really needed to make sure that service topology as a enhancement proposal and as a concept was flexible enough to address all of these different use cases. You can see here that the KEP for it was accepted back in December. It took a little while to kind of discuss that and to finalize the KEP, there was a number of months after that where there wasn't a ton of work that was going on in public, but it turns out that there were some, a PR was posted relatively recently and merged last week. Just in time for 1.17, I believe, that adds some of the initial bits of service topology to the various parts of Kubernetes, including the proxy implementation. So what does service topology actually do? First, we can back up a little bit and say that we do have kind of an implementation of service topology in Kube Proxy already, and that was a tag that allowed the proxy to direct traffic to a pod that was on that particular node. So that's kind of very basic, but obviously it doesn't address some of the needs that other contributors had for locality and service topology. So the KEP adds a key to services that, a topology keys to services. And each of these keys, they're fairly well-defined keys. And there's only a couple right now. But I expect there will be more added in the future as we have better ideas of exactly what topology means in different cases. The proxy implementation then takes a look at the service itself and tries to match the labels on the service with particular labels on the node. So at this point, it's mostly node-based. And it turns out that topology labels on the node itself. It matches them in preference order. So if you have, you want to try the host name first, and if the host name doesn't actually have any matches, then it will also try to match things like availability zone and kind of go on down the list. So it really is under the control of the person writing the service and to some degree of the cluster when it decides what keys to put on each particular node. There's also future enhancements. There will be a pod locator resource. It turned out that there were some scalability issues with the current implementation, and so the contributors working on service topology will be adding the pod locator resource to help address some of those issues around how you actually do the matching. And last, I think we have SCTP, which is Stream Control Transmission Protocol. It's actually more of interest to, I think, more telephony applications and telcos, because that protocol is very heavily used in some of those industries. And if you're not familiar with SCTP, it is basically like a mashup of kind of TCP and UDP with some additional features for reliability and redundancy. Kubernetes only supported, up until a couple of releases ago, I believe, TCP and UDP for a lot of the service and ingress and other operations. And it turns out that as Kubernetes is trying to enter new worlds and enter new industries and businesses, that SCTP was something that quite a few users actually were interested in having support for in Kubernetes. So the implementation sits alongside both the TCP and UDP bits as a core Kubernetes protocol, and that shows up in a lot of different places in the code. So the one place that it might show up that most of you might be familiar with is in the service, and you can kind of say that this service has a particular protocol attached to it, and that is the protocol that I want to have the proxy pay attention to when it needs to move the traffic through the cluster to a particular backend. So SCTP is now one of those protocols that you can add to your service, but that also means that we need to take that and move it through from services to also endpoints. We need to add support to host port for that, and then of course network policy as well. So the actual protocol does touch a lot of different places in Kubernetes. The support's actually been there for a while, and it was alpha in Kubernetes 1.12. And we've been finalizing some of the rest of the KEP for that, and we hope to possibly make it beta in Kubernetes 1.18 sometime early next year. It needs a little bit more of a push over that finish line. The other thing to note is that if you are developing a network plugin that, a CNI essentially, you will need to add support for SCTP to that network plugin if you can, to take advantage of some of these features.
Okay, we're standing between you and lunch. So in conclusion, what does this all mean? So for endpoint slice, we're basically enhancing the API to support massive scale services and endpoints. In terms of the API work on ingress and service, it's going to be better L4, L7 modeling, and then raising the bar in terms of features and extensibility. Dual stack, basically, you can use IPv4 and IPv6 in your clusters. Service topology gives you control over interzone region traffic. Well, not just that, it's a very generic thing. And then finally, SCTP support gives us protocol support completeness. And that's it. So Q&A, and this is where you can find us. Vallery also had a slide like this, but we'll keep this up here. And someone over here. Where are the slides? Where are the slides? Oh, they are posted as a PDF. Oh, no. That's, maybe Tim can do it, or Vallery, because we were not on the speaker thing. Send it to who? We can work it off offline. Here.
Thanks for the deep dive, gentlemen. Scott Fulton from ZDNet. A question about the IP family attribute. Anyone here in the audience could tell the difference between an IPv4 address from an IPv6 address just from looking at it. So it's obviously, this got colons in it, for heaven's sake. It's not IPv4. And so my first thought is, do you really need an explicit attribute saying the following is an IPv6 address? And then I remembered something that you were saying about the time things take in parsing and the performance attributes that you wanted to give to it. Is that attribute explicit just to save the CPU the time of actually having to look at the first, second, third characters and say, is this a colon? If so, then IPv6?
That's a great question. I'll say right off that I'm probably not the full expert on this, but I'll say one key reason to have IP family is just for the sake of validation, to actually ensure that in say an endpoint slice or whatever, that all addresses match a specific IP family. But Tim can give more background.
So that's a really insightful remark, because the first version didn't have the distinction. The second version did. And the reason we added the distinction was, in fact, what we noticed as we were adding dual stack support is we were going to ask every node in the cluster to run through every endpoint and parse it and make a decision about whether it was v4 or v6. Right? And that seemed like a really redundant, silly thing to do when we know that it's cache inefficient to do that. There isn't a simple API. I guess we could write one. But the simple API was go parse this IP. So it's going to walk through the whole thing for every IP address times 5,000 nodes times, and it blows out really quickly. And we can't do anything about it early. Whereas if we go this way, which I really wasn't a fan of, but I came around to, now I can validate it a priori on the API server and split those out with no work being delegated out to every node. So we took a little bit of a hit on the API in order to save a bunch of work in the nodes.
Thank you. Someone over here? Go ahead.
Okay, so in the meantime, the related question is the IP family. So it has, as we see, it has two IPs. Can it be a case where I have both the IP as IPv4? What I'm coming to is multi-IP support for the pod. Can it be extended, or is there a thought that the same construct can be extended to support multi-IP pods?
You guys are relentless. The short answer is yes. We've made sure that the design accommodates this, knowing that this is a likely direction to go. I don't know exactly what that means yet. There's been a bunch of work that Dan and others have done in the community around having multiple interfaces on a pod. You now have a way officially that you could represent it, although you would blow up a bunch of controllers. But the logical extension would be, okay, let's make it possible to actually do this. I think we don't yet have a broad definition of what that means. If I have two IP addresses in two contexts, like for a controller, how do I interpret those? One of the things an astute reader will have noticed is that we left room in the API for metadata on each IP address. So the IP address is not a list of strings, it's a list of structs where one of the members is the IP. So we have room for metadata that we can use to decorate this. So we've left ourselves a vector for doing this, but we haven't done it yet.
It needs a lot more discussion, too, to figure out exactly what that really means. So if those are things that interest you, please come to the SIG meetings, and let's discuss it, and let's make a cap for exactly what this should look like.
Maybe I missed it. What was like the purpose or the problem that you're trying to solve with endpoint slice? Like, were there endpoints that weren't needed that were being sent down, or like why is it expected that it's helping?
Can you say that one more time?
What was the problem that you were trying to solve? Like, I know you said scale, but like if you still have to get all of the endpoints,
Great question.
Is it helping, or were there unused endpoints that you were getting because it was like a bulk API?
Yeah, that's a great question. So the problem with the endpoints resource is that the full resource had to go across the wire when a single endpoint inside that resource changed. So a single IP changes in that endpoints resource, the whole thing goes across, whereas an endpoint slice, that whole thing is a whole lot smaller. Bowie, up here.
Oh, I saw someone over here.
Okay.
Load balance.
Thanks. Okay, so is there a reason servers can't be both v4 and v6 so that you could have a friendly name, and if it's a v6 service or a v4, it'll be able to choose what it goes to? And then a follow-up question is there any thought in making opt-in for v4? So like by default, every pod gets a v6 address, but it opts in to get a v4 address also?
So on the first part, we did that mostly as a shortcut. We thought, we looked at the use cases that we had in front of us, and we didn't have a concrete use case for having a single service on two families that wasn't also solvable by having two services. The friendly name, like we talked to a few customers and users, and the friendly name didn't seem to be enough of a motivation to take on the complexity of doing both at the same time. We're still open to it if we find the use cases and the demand for it. The second question, I think, is not something we put a lot of thought into, honestly. We left that at the network level for the CNI to decide. So
Yeah, so for the second question, Kubernetes supports IPv6 single stack. So I think a lot of the functionality is there to not get v4 if you don't want v4. But that said, it's going to be single stack throughout your entire cluster. At this point, we don't really have a way of saying that some pods should only get some address or some family, and some pods should get others. You can't really necessarily mix it up. But I think we'd probably like to get there. We just need to kind of keep going through all of the bits and APIs and components and make sure that they're okay with that. I don't see any particular block for that kind of behavior. It's just that's like phase 6.
I just had a quick question about the endpoint slice thing. You mentioned that there was a condition on each endpoint slice. Is the sort of intended use there to be like replacing the old endpoint instead of having the like ready and not ready in a single condition? You'll end up with 2 endpoint slices, one that has a condition of ready and one that has a condition of not ready. Is that the no? Okay.
I'm scared of this thing. So yeah, the question is great. Right now, an endpoint is either a single endpoint referring to an IP is either ready or not ready, and there's some deduping involved, and I think we lean towards, if there's 2 that come in that are conflicting, we lean towards ready instead of not ready, but I'd have to double check the code. But there is only one representation of an endpoint is the goal, so we don't have 2 different ones that are ready or not ready.
With the introduction of IPv6 and dual stack, when do you see the phasing out of all the strategies to like VPCs and everything? When do you see that coming so it's easier for the user just to have one IP and a publicly addressable IP?
I don't know that we've really made that a goal. Most of the users that we're talking to today see dual stack sort of for the indefinite future. There have been lots of conversations around NAT and NAT4.6 and other encapsulations to make it less complicated, although you just push the complexity somewhere else. We haven't had a conversation really about like what is the ultimate end goal of v6. At least if there has been that conversation, I haven't been part of it. But again, like with all these questions, like they're great. We'd love to hear requirements if people think they have ideas for what we should do.
Thank you. I'm not sure if it was mentioned in the presentation, but is there an API backward compatibility strategy for moving to dual stack?
The API compatibility story I'm actually pretty proud of. We spent a long time working on that. Mostly it works the way you would expect it to work. And to do that, we had to sort of define what we thought the various use cases were with old clients and new servers and converting from old to new. And we explicitly called out all the different edges. So if you have an old client and you only know the singular IP address and you mutate that IP address, we'll sync it into the 0th entry of the list. If you know the new API and you write the list but not the singular, then we'll sync that back out. We can tell which changed on an update. And if you change them both and you change them incompatibly, then we'll actually fail the API call. So mostly it's going to do what you expect it to do if you have a dumb client, and if you have an enlightened client, it'll be the same.
Oh.
Oh, and yes, and it's sort of as the tiebreaker, if we get stuck with both, we choose the v4. But that's a really corner case.
So one question about the dual stack. So the dual stack Kubernetes allows to consist the cluster with the IPv4 only host with the IPv6 host, or in case of when we create a dual stack, at that time all node should support the IPv4 and IPv6.
The assumption now is that all nodes are dual stack, right? And we're willing to see where this goes now, right? We defined the first 3 phases. We're still in the middle of implementing phase 3. I assume that there's probably 10 more phases beyond that as we figure out more and more of the user requirements.
Yeah, this is not an IPv6 question, so it's related to the changes to the gateways, route, and services. Do you think that this change or this proposal may restrict extensibility to other use cases? Because, like, I feel that the Ingress concept is abstract enough, and you can introduce several other use cases, but with the gateway routes, it feels like you are restricting into a certain model that might not be extensible. I don't know.
So that's a good question. You should definitely contribute in terms of your use cases, and that's kind of, we're at the stage where we're sort of sketching a framework and then collecting the use cases and making sure that the mapping is okay. One thing is that if you find that Ingress is perfectly valid for your use case, then it still will exist and be supported as a GA API. So that thing will never be deprecated or removed in favor of the new API.
I hope that everything you can express in Ingress, you can express better in the new Gateways plus Routes API. The thing that got me excited about the new API is I see the ability to represent the lower level, like L4 things that Service does. Like Service is a terrible API. It's a bunch of different concepts that all got glued together into a single resource. I see this as a possible way of breaking that up so that we can actually have a cleaner API to the L4 constructs also. But if you can think of a use case that is representable in some other way that isn't in the gateway system, then we want to know. And we're explicitly adding a bunch of extension points so that people can take their implementations and do crazy things without resorting to annotation.
Thank you. That's another question about the kind of the evolution of Ingress that I think segues on from that. As well as better being able to express the separation between L4 and L7 constructs, is there any thought to opening up Ingress to a wider range of L7 protocols? There are other L7 protocols in HTTP have got analogous concepts of stuff you want to do on Ingress. Is there any thinking of that?
Yeah, so you should look at the sketch to see that that was one of the provisions we want to add in, is that not just HTTP routing, but different other routings. There are a number of ideas floating around out there, the most important of which is you just simply are able to specify the protocol, which I think doesn't quite exist today in any official API.
But remember, one of the extension points is in the routes resource. So you can actually, like in theory, you could build your own traffic management system that routes the, some traffic from a gateway into a MySQL route, or whatever crazy route you're thinking of in the back end, and that doesn't actually need to be standardized by us or by anybody. You can go do your own thing via extension CRDs. That's one of the objectives.
Yeah, thanks for the talk. I just wanted to ask, I guess in retrospect, if you could kind of go with this alternate reality with kind of the information you know, how would you go about doing the Kubernetes networking different? Like Tim, you mentioned kind of getting rid of services or kind of changing it up. Are there other components that you kind of get rid of or tweak or just not think about in general?
Services is my biggest one.
Yep.
It's become really complicated to think about how to add anything to service because of the way it intersects with all of the other things in service. And there are known bugs, for example, in the REST logic around service where immutable fields become mutable if you do the right sort of ballet dance. And they're really hard to fix because of compatibility reasons. So yes, I would love to burn service to the ground and start that one over. Ingress was originally designed sort of to be what Bowie is describing here, but we didn't have the follow through or the sort of the vision to see how to do it correctly. Also, we didn't have CRD at the time, so that made it very difficult to think about extensibility that way. So yeah, knowing what we do now, I think those are the two biggest things, sort of orthogonal inputs to services and higher level extensibility. And maybe more omnibus network driving. Like the network drivers right now are kind of spread all over the place. There's the CNI driver, a little bit of logic in kubelet, there's kube proxy, there's your network policy, and they all sort of do things that interact with each other in sort of poorly defined ways. If I could go back, I might up-level that once.
Oops. All right.
So for the new features we introduced, any be impacted with the service mesh anthos you guys doing, such as features endpoint slice and Ingress, how it been affected to the service mesh you are offering?
The gateway stuff is explicitly not about service mesh. A lot of the concepts overlap, but we're really focused on Ingress, sort of what we traditionally call north-south. That's the feature set that we're focused on. Some of the service mesh implementers are participating now or are talking about participating, and they're looking at whether this API can define sort of the service mesh API. And in fact, I did a talk this weekend at the Rejects conference on this topic a little bit. But service mesh is explicitly not the goal.
With regard to endpoint slice, I do know that people are looking at it basically as these primitives from Kubernetes get a little bit more sophisticated. There might be a lot of reuse, just then you don't have to maintain two APIs that do kind of the same thing.
Yeah, that's a great point. The thing I've been thinking a lot about in the last couple of months is incremental adoption, making it easier for people to sort of grow from basic use cases into more advanced use cases. And frankly, Kubernetes has made it very difficult to sort of evolve your usage of Kubernetes. You hit the end of the runway on service, and then you have to stop everything you're doing and move into Ingress and change the mechanism and change the controller and change the API and go retest and requal and benchmark. And then you can carry on sort of where you left off. And then when you run out of the Ingress run map, you have to go into like a service mesh, and you do the whole process over again. So I've been thinking a lot about how to make more incremental adoption, and I think actually the Gateway API is a path towards that, where you can start with your gateway, and when you hit the end of the capabilities there, you can change the class. And now your class becomes an L7 class, and suddenly you're able to add more functionality through the extension points, but you never had to go back and rewrite your API, right? And so this is sort of my interest in it, and I'm keen to drive on that model, and every time I talk to people, they sort of nod their heads and they get it. I hope we can deliver that.
Sorry, one last question.
Okay. Currently, I'm a part of a container network interface feature team. Currently we are watching on the endpoint resources, and we are creating, based on that, we are creating endpoint files, and based on that we create flows. So we use OVS switch to program the flows. So basically we watch on the endpoint resources. Now that endpoint slices are coming, so what are this, still the endpoints will be there, the way, how do we watch for the resources?
What's the transition plan, Rob?
Yeah, that's a great question. I meant to cover that in more detail in the actual talk, but endpoints will continue to exist for the foreseeable future. Of course, if you want improved performance, greater scalability, use the endpoint slice API if at all possible, but endpoints will continue to exist and provide that backwards compatibility for a long time.
Thank you to everyone. If you have more questions,
To add one more